What is the unit of Hz in radio waves? In radio waves, Hz is the unit used to measure frequency. Frequency represents the number of cycles that occur in one unit of time, typically expressed in cycles per second or hertz, Hz. Therefore, Hz signifies the number of cycles occurring per second. For instance, a wave with a frequency of 1 Hz completes one cycle in 1 second. A wave with a frequency of 1 kHz, 1000 Hz, completes 1000 cycles in 1 second. The frequency of radio waves varies depending on the type and purpose of the wave. For example, the frequency range for FM radio waves is typically 87.5 to 108 MHz, 108 million Hz. Microwaves operate in the frequency range of 300 MHz to 300 GHz, 300 billion Hz. The frequency of a wave influences its characteristics. Higher frequencies result in better directivity and shorter wavelengths. Conversely, lower frequencies lead to reduced directivity and longer wavelengths. Utilizing different frequency ranges allows the creation of various communication devices. Examples include FM radios, TVs, mobile phones, and the Internet, all of which transmit information using radio wave frequencies. So, in the case of 5G, how many times does it repeat per second? The frequency bands for 5G can be broadly categorized into FR1 and FR2. FR1 utilizes frequencies below 6 GHz, often referred to as sub-6 GHz. The frequency range for FR1 is 16 GHz, with examples in South Korea including 2.3 GHz, 3.5 GHz, and 28 GHz. FR2 employs frequencies equal to or above 6 GHz, also known as MM wave. The frequency range for FR2 includes 2440 GHz, 6080 GHz, 80300 GHz, with South Korea using frequencies such as 24.25 GHz and 26.5 GHz. Therefore, the relationship between the frequency bands of 5G and Hz is as follows. For FR1, since the frequency range is 16 GHz, you can calculate the corresponding Hz by multiplying the frequency in GHz by 10 to the power of 9. For example, the frequency of 3.5 GHz corresponds to 3.5 GHz 10 to the power of 9 equals 35 billion Hz. Thus, it repeats 35 billion times in 1 second. For FR2, with a frequency range of 2440 GHz, the calculation is similar. For instance, the frequency of 28 GHz corresponds to 28 GHz asterisk 10 to the power of 9 equals 28 billion Hz. Consequently, it repeats 28 billion times in 1 second. In summary, for 5G, the repetitions per second range from 1 to 35 billion, depending on the specific frequency band. So does this mean that the wavelength is longer compared to MHz? You mean short? Hz is the unit for measuring frequency, and wavelength is inversely proportional to frequency. Therefore, higher Hz values correspond to shorter wavelengths. Since MHz represents 1 million Hz, the wavelength of 5G frequencies is relatively short compared to MHz. For example, the frequency range of FM radio is 87.5–108 MHz. The wavelength corresponding to 87.5 MHz is approximately 3.4 meters. In contrast, for one of the frequency bands in 5G, 3.5 GHz, the wavelength is about 0.86 centimeters. Consequently, the wavelength of 5G is approximately 4,000 times shorter than that of FM radio. In essence, 5G has the advantage of shorter wavelengths compared to MHz, resulting in better directivity and lower signal loss. However, it comes with the drawback of being more susceptible to signal blockage by buildings and structures. So, does a short wavelength mean that radio waves are more likely to be blocked by obstacles, and if the wavelength is longer, it is less likely to be blocked? Yes, that's correct. Shorter wavelengths, as seen in MM wave frequencies used by 5G, result in better directivity but also make the signal more susceptible to blockage by obstacles such as buildings. On the other hand, longer wavelengths have lower directivity but can better penetrate obstacles. Because 5G operates in the MM wave frequency bands, it has short wavelengths, making it prone to signal blockage by buildings or structures. To overcome this challenge, 5G networks deploy a large number of small cell stations to extend the reach of signals. Moreover, 5G employs beamforming technology, enabling the concentration of signals in a specific direction. This capability helps reduce the impact of signal blockage by obstacles. Through beamforming, 5G can focus its signals where needed, enhancing overall communication performance. Is it advantageous to transmit a lot of information such as image quality if the wavelength is short? Yes, shorter wavelengths are advantageous for conveying a lot of information, such as in image quality. The bandwidth of a wave is inversely proportional to its frequency. Therefore, higher frequencies result in wider bandwidths, allowing for the transmission of more information. For instance, the FR2 band of 5G operates in the frequency range of 2440 GHz, providing a bandwidth of 210 GHz. In contrast, LTE utilizes frequencies ranging from 600 MHz to 3.7 GHz, with a bandwidth of 0.53.5 GHz. Consequently, 5G has a wider bandwidth than LTE, enabling the transmission of more information. This translates into better performance in aspects like image and sound quality, response speed, etc. Indeed, 5G is known to be suitable for high-quality, high-speed data transmission applications such as 4K and 8K UHD videos, VR, AR, and real-time streaming. The relationship between wavelength and energy is also crucial. Shorter wavelengths correspond to higher energy levels. Therefore, waves with shorter wavelengths can convey more information. For instance, FM radio, operating at a frequency of 87.5 MHz, can use a bandwidth of 100 kHz per channel. On the other hand, 5G, with a frequency of 3.5 GHz, can use a bandwidth of 100 MHz per channel. This means 5G can transmit approximately 10 times more information than FM radio. In the case of 5G, it uses wave frequencies with short wavelengths, allowing for the rapid and stable transmission of diverse information like image and sound quality. However, a drawback of shorter wavelengths is their susceptibility to obstruction. To address this, 5G deploys numerous small cell towers and utilizes beamforming technology to focus the waves in specific directions, minimizing the impact of obstacles.